Okay, then maybe we can start. So yeah, welcome everyone, and welcome back after the Easter break. So maybe I first say a few words about the exam. Of course, it's still a bit preliminary because yeah, of the Corona situation, there might be some changes. But for now, I mean, as I already announced in the beginning, it will be kind of an oral exam in the same way as we had it last year, except that now we'll do it remotely. I mean, this is most probably, and so yeah, the main core will be the proof ideas and the statements and the main things that we discussed this semester, and yeah, it will most probably be that we will use Zoom, and then we will ask you to maybe use your phone as a document camera and then write your answers on the. So we'll give you questions like last semester, and then you should write them on some piece of paper, and yeah, then we'll have some discussion about this. But yeah, as I said, this is still a bit preliminary and might still change now. The situation is getting better, so maybe we can also change the format. But I'll keep you posted. Okay, so that was about the exam, and then maybe I will start with some. I'll start now recollecting a little bit what we did before Easter. I guess the main two things were that we defined what so yeah, some recollection. I don't want to go into too many detail, and I just picked the two maybe most important definitions. So so we defined what the integration with respect to Brownian motion is. So yeah, I hope you all remember what Brownian motion meant and some special Gaussian process. And so yeah, maybe here I should start with the following setup. So I assume that the probability now ds, so I take a stochastic process, and then I assume that this integral is finite with probability 1. Then, and there are some conditions, there's some filtration, and but yeah, let's omit this for now. So just to recollect the definition, then this integral was somewhat the limit n to infinity, and then I approximate this integral by sums, maybe in this form, gx k over n b t k plus 1 over n bt k over n, right? And this is the definition, and the limit exists in probability. And yeah, well, maybe just to be complete, so the other assumptions that I omitted were that I have a filtration ft, such that the following holds. So x, maybe it's better s, and then I assume that xs is fs measurable, and I assume that bs, so that's a Brownian motion. Yeah, maybe I should say Brownian motion bs, and bs is an fs martingale. I just wanted to pick out these most important definitions. So yeah, so this was our assumption here, and then this was the definition of the integral, and then you had kind of usual linearity rules. And then I should make here a remark. I should correct something, namely there was yeah. So in lemma we had the lemma 3-4, which was the properties of this kind of integral, and then lemma 3, 4, 3i, and 4i. They need a little bit stronger property. Maybe they need that the integral, that the expectation of this integral here is finite. Xs squared ds. The expectation is finite, which is of course some stronger property than just this here, right? And so need that this is finite, and yeah, maybe I should just state them again. All t. So what did they look like? So 3i was that this process which I get by integrating this here is a martingale. With respect to this filtration f, well, maybe ft now. And 4e was this E to isometry property. That should be a big S. Xt pt squared. So if I take such an integral, I square it and I take the expectation, then that's the same as if I take the expectation and then I integrate from s to t xt squared, but then dt. Okay. Okay, so these were the two properties, and they need this stronger property, this stronger assumption, which I need, which I forgot last time. Okay, so that's what I wanted to say again about the integral, and then maybe the other interesting thing, or the other most important thing that we used were this stochastic differential equations as maybe you should take a picture now. And yeah, I just want to recall the scalar case. Well, maybe now scalar case. And they were formulated in terms of an integral equation. So what does that mean? So it means that if I have something of this form, maybe bt xt dbt plus u xt bt, then this is by definition that means that x of t is equal to x0 plus integral from 0 to t vs xs es plus 0 t us xs ds. Right, so that was the kind of stochastic differential equation. Now I wrote everything in the scalar case to make it a bit simpler, but it's, I guess, obvious how this generalizes, and yeah, how this generalizes, and then under certain assumption on the v and u. So basically that they should not grow too fast and they should be Lipschitz continuous. That's somehow a bit in the same what you might know for differential equations, for the deterministic differential equations. They also have these kind of conditions, and under these conditions we had existence and uniqueness of strong and weak solutions. So where the strong solutions mean that you a priori fix the filtration and the Brownian motion and the probability space, and then you construct, or strong solution is then a solution with respect to this given data. And the weak solution was that you, for a weak solution, you were allowed to change the Brownian motion and the probability space and the filtration. So a weak solution is in some sense, yeah, well, obviously something more general, and there you can choose the probability space or the kind of probabilistic data that you want to use. Okay, and so yeah, well, maybe I just say that we have some existence and uniqueness results. As we discussed last time, I think it was theorem. Yeah, maybe theorem 311. Under some assumptions on V and U. Yeah, maybe I should just briefly recall them. So the main thing here was that, I mean, I now do the scalar case, UTX, that they're smaller than, that they grow at most linearly. Well, of course, I can have a constant here, and that they're Lipschitz in the X variable. So y, same for you. Okay, so these were the main assumptions that we used there, and then they guaranteed that we have a solution, and that this is also unique. Okay, so that's what I wanted to say here, and then yeah, maybe I'm not sure whether I already gave some references. Yeah, for the stochastic calculus and things, and stochastic differential equations that we used here. So I guess the two books I used were mostly, I think it's pronounced Oexendal, stochastic differential equations, and that's kind of quite general. That's somewhat a good introduction. So they introduced these notions of stochastic calculus that we also introduced, and then basically they start in such a way that they introduce everything in such a way that they can most quickly come to this stochastic differential equations. And then sometimes somehow for this existence and uniqueness results, I think I went to this Scarazas Schreve book. It's a bit older, I think. Brownian motion. And stochastic calculus. Okay, so yeah, maybe this is a good time for a picture. And then yeah, today I'll first introduce one more concept, the so-called stopping time, which is very important in this stochastic calculus business. And then I will formally write down these statements that I sketched at the end of the last time as an outlook, and then they're the main results of this section 3. And then I will start going into the proof there, and yeah, then we'll see how far we get. Okay, so yeah, as I just said, so there is one more notion which I would like to introduce. This is so-called stopping time. And yeah, I'll basically directly go into the definition and then explain a bit what it means. So I think it's definition 313. So as always, we start the filtration. And then we consider following type of functions. So it's a function, well, yeah, I call them tau, which maps the probability space into 0, infinity. This is called stopping time. And yeah, as always here, it's with respect to this filtration. If the following holds, so if I take tau and I look at the event where this is smaller than t, this should be in ft for all t bigger than 0. And yeah, well, just to be precise here, this is of course those omega and omega that such that tau of omega is smaller than than t. So what does that mean? So well, that means that if you want to decide whether tau has already occurred or whether tau is smaller than t, then it's enough to know the information in the set ft. So yeah, maybe it's it's easiest to explain it. So the typical example looks as follows. So you have some process. Well, maybe let's just start with a Brownian motion. Brownian motion on R, and ft is a filtration such that the bt is adapted, so such that bt is ft measurable, all t. And then the natural thing is, well, and yeah, a is somehow in R, then a tau, which is the infimum overall S, and then such that Bs is bigger than A. This is a stopping time. With respect to this filtration Ft. Okay, so that's the natural thing. So the natural, or that's a quite, well, these are maybe also sometimes also called hitting times. So what does that say? Well, you want to look at the first time where your Brownian motion exceeds a certain A. So well, maybe I can try to draw some realization. So this is the t, and then here I draw a bt of 1 fixed omega. So of course the b starts in 0, and then it has some crazy movement. Well, maybe not too nice. Okay, and then maybe I fix a point A somewhere here, and then tau A would be here, tau A of omega. Okay, so that's the first time that your Brownian motion is bigger than this A, and yeah, of course here you can always you fix a time somewhere here, then of course you can always decide whether this already occurred just with the information that you had before. So that sense it's measurable, and yeah, and I guess I'll make a homework out of this too, so that it's a bit more transparent what happens, and that you get some experience with this. And then one important property which we will use today. Yeah, maybe of course now is a good time to take a picture. And then I need one auxiliary result about such stopping times, and in particular, when I evaluate an integral up to stopping time. Okay, so let's look at it as follows. So let's take a deterministic t. And tau is stopping time. Yeah, and then I should say that it's with respect to some filtration. Ft, and I assume that that tau is smaller than t, almost surely. And xs should be a fs should be fs adapted, so it's a stochastic process such that I can integrate it. So I need that the integral from 0 to t xs squared ds is smaller than 1, almost surely. And yeah, maybe I should also fix a Brownian motion. So yeah, and yes, yeah. Brownian motion. Yeah, which is a martingale with respect to this filtration. With respect to ft. Okay, and then the important thing that I want to say is that if I integrate up to tau, my process xs with respect to this Brownian motion, then I can do it as follows. I can also integrate up to t and just add the characteristic function that the s is smaller than tau. Yes, right. So this is of course again a stochastic process, completely well-defined stochastic process. Of course, this condition is true, so I can make sense out of this integral. And this integral here was already defined before. So yeah, so that's somehow an identity we will use later. And so in fact, we will use it in the, yeah. So that's the main thing I want to use here about stopping times. And yeah, you should see them as they are always used to, yeah, in such situations where you want to control a stochastic process up to a certain event, up to a certain time, when some special condition is maybe starts to be violated, and that will always help you to then analyze the situation much more precisely around this time if you introduce these stopping times, and then you, yeah, we will see some typical kind of arguments of these things today. Okay, so yeah, maybe now you can take another picture. And now I want to go to the core results of this section. So yeah, I hope you took this, and then so that's that 3.2. This is about results about Dyson-Brownian motion. Oh well, maybe more about its existence. Okay, so maybe just to give you an idea. So the main results of this section 3 are the theorems that we will state now. Theorems 315 and 316 that we will state, that I'll state next. First, I will define some subset of Rn, which I already defined last time, I think. I want to denote it by sigma n. That's the set of vectors in Rn such that lambda, the first component, is smaller than the second, smaller than the third, and so on. It's smaller, strictly smaller than lambda n. So it's the set of n vectors with strictly increasing entries. Okay, and then the main theorem, or this theorem 315, now says the following. So I take a beta bigger than 1. So I mean, this beta already appeared last semester, right? This gives you the information on so you should think of the case beta equal to 1. Then we are studying real symmetric matrices, and if beta is equal to 2, then we look at complex Hermitian matrices. And I want to start, and I also fix the vector lambda 0 in the closure of this set sigma n. So that means its entries are non-decreasing. So there can be some entries can be the same, but at least they're ordered. Okay, and then I have the following result. Then there exists a unique strong solution lambda t bigger than 0, and that lies, well, in the, you can write it like this, continuous functions that time runs from 0 to infinity up to, and the values are in sigma n closure. And then I have this of the following family of system of stochastic differential equations. I will call this system DBM. So I have lambda I is equal to 2 over beta n square root dBi plus minus lambda I over 2 plus 1 over n sum j runs from 1 to n. J is different from I. 1 over lambda I minus lambda j dt, and I runs from 1 to n. And then, the initial condition is obviously this lambda 0. And here I should remark that I always lambda I is of course the components of the lambda t. Well, maybe it's a bit more transparent if I add the t dependence. And the B1 and up to Bn are independent Brownian motions. Okay, And yeah, note that it's very important here that here you first have the lambda I and then you have the lambda j. So this sign here, so well, of course, if you change the order, then this sign would change, but that sign here is really important, that as we will see in the proof. There's some other nice property, namely that for every positive t, the lambda t will actually be in sigma n. So there will not be any coinciding lambdas for all positive t. And the lambda t depends continuously on the initial solution. Okay, so yeah, maybe now it's a good time for a picture. And if I have such a solution lambda t, then this is this I will call Dyson-Brownian motion, and this will now basically the whole rest of the course will be about studying properties of this SDE. And yeah, so maybe I should note this. So solution lambda t bigger than 0 to the system dBm is called Dyson-Brownian motion. So in some sense, this is Brownian motion on eigenvalues in the way it's interesting for us. Okay, and yeah, maybe before I continue, I should give you some idea about how you should think about this equation and what are the special terms doing. And yeah, so I mean, maybe I should give you some heuristics about terms in the dBm. So now this is going to be a bit more physical in some sense. So the first thing what we'll do now. So we want to think of lambda 1 up to lambda n as particle locations. So and then these particles will have certain interactions and follow certain. So I mean, this will be helpful for people that have some physics background. I guess most of you are in this master class as particle locations in R. So then you will get a bit better feeling, but of course it will be not will be helpful for the math that follows, but I will not use this. So so yes, so the lambda 1 up to lambda n are now particle locations of n particles that live in R, and then these terms in the terms in here they have different kinds of interpretations. So first of all, this first term, the dBmi term, is what's called a diffusion term. So in some sense that's a random motion. So let me say a word about this. So what does that mean? So well, this means that that this term here changes the particle in such a way like you would have a pollen in a water or in a solution. So that's some kind of random motion without orientation. And here it's also important that for each particle I, so for the ith particle, the motion is independent of the motion of the other particle. So really, each particle wiggles a little bit around the location it's currently at. And that's in some sense what this term does. and then so that's some kind of random motion which doesn't have any direction. And in contrast to that, there's the other term which ends with a dt. That's what's called the drift term. So and that's a deterministic motion. This should also in quotation marks. Deterministic motion which originates from the particle location. Yeah, so well, here you see in some sense there's no additional randomness in there. And just if you have one particle configuration, so lambda I up to lambda 1 up to lambda n are fixed, then this defines you some force that acts into a certain direction. Well, either it can make the lambda I bigger or smaller. Lambda I is only a real number. And then there are, in some sense, two kind of terms. Namely, there's this this first term here. So the lambda minus, the minus also important here, minus lambda I over 2 dt. That's in some sense that gives you some kind of confining potential because it avoids that the particle locations become too large, right? So avoids that particle escapes to infinity. So where this means plus or minus infinity. So why is that? So imagine the particle lambda I would become very large. So say lambda I would go to plus infinity. Then here you would subtract minus lambda I over 2. So that gives you some force which pulls you back towards 0. And the same is if lambda I would go to minus infinity, then it would also pull you back to 0 because then that would be a very big term, which makes the lambda I, which makes it bigger in the sense that it goes back towards 0. And then there's another terms. There are these terms 1 over lambda I lambda j, and so maybe I should write it like this. So there's a plus which is important, and then j is different from I lambda j dt. So that's in some sense a repulsive interaction between those particles. Interaction. And yeah, let me illustrate this to you. And then note that the lambda i's are ordered. So that means so of course this here is interesting only if if lambda I and lambda j come close to each other, and in some sense it's always two neighbors that come close to each other. Well, what is my idea? Ordered. Okay, ordered, and therefore if two particles are close to each other, then there are two, let me call them neighbors, lambda I plus 1 that are close. Yeah, I hope that will tell you to take a picture of this part maybe. And then another one of what I wrote up to here. So yeah, so I now have so as let's assume that two of them are close. So lambda I plus 1 minus lambda I, that's positive. This is, let's say, much smaller than 1, so tiny. Maybe it's, I don't know this. Then I have the following. So let's assume we have this picture here. So maybe I draw it here. So there's a lambda I plus 1, then there's a lambda I, and of course somewhere here far outside there is a, let's assume that they're much closer than the other neighbors. I minus 1. It should look like this. Okay, so they are now all on the, or they're all confined on the real line. And now I want to see what's the effect if two of them are very close. So then, of course, the only term that will matter in this whole sum. So then I have lambda I. There's the random term and the confining potential term, these things. And then the dominating term will be this one. So lambda I minus lambda I plus 1 et. But now this is small, and this is, of course, always negative, because the lambda I is the, so the denominator is small and negative. So this whole thing together is negative and large. In modulus. So that means that then the lambda I should decrease, right? Because the derivative is negative and large. Maybe I use some color here. Lambda I decreases. They're small, so that means I get some force that goes towards the left. And then I have a similar behavior in the d lambda I plus 1. There again, the dominating term is the lambda I plus 1 lambda I et. Now this is positive and large. Sorry, it's not readable. And then as before, well, maybe I take another color. Hopefully green is readable. So this means lambda I plus 1 increases. So there's a force acting here towards the right. Yeah, and I should maybe say this is the dominating term. Okay, so that somewhat explains why it's a repulsive interaction. So maybe I should, yeah, maybe you can, if you want to take another picture of another picture like this. So so what did we see now? So yeah, this is of course an interaction, because it's it tells you how the different particles change each other when the location changes. And then I wanted to see what happens if there are two particles coming close. So that, but then because they are ordered, I can assume that actually two neighboring particles, let's say lambda I and lambda I plus 1, are close. So if such a difference here is small, then I have two effects. So the lambda I will decrease. so it will be moved away from the lambda I plus 1, and then and the lambda I plus 1 also increases, so that will also be moved away. That's why it's called repulsive, so they repel each other and move each other away from them. And then, of course, if they become too large, then again the confining potential comes in. Okay, so and then after the break, I will state the other theorem, the 3.16, which will give you a way how to, where we will see that if we have a special kind of stochastic differential equation on a matrix level, on a Hermitian matrix, then we will see that the eigenvalues will be a solution to this system here, and that's what we're interested in. And then after I stated this, we will go into the proof, and starting with the proof of 315. Okay, so if you have any question or comment, then let me know, and if not, I would suggest that we make a break till 10:15. Okay, then I think we can continue. So yeah, what I already said before the break. So so far we've had a theorem which tells us something about the solution, well, or at least the existence and uniqueness of a solution of this equation. And now we want to see how we can actually construct them in the random matrix context. And yeah, the main example will be here that there's a specific, well, a quite natural evolution on the space of, say, Hermitian matrices, and under this evolution, the eigenvalues will follow this equation, and that's the statement of that's the result of the next theorem. But first, I have to introduce this evolution on the matrix level. So that's now that's the next thing. We now consider for HT, which is want to denote its entries by HKLT. Sorry. So K and L run from 1 up to N, and we consider the following matrix valued stochastic differential equations. Okay, so they look as follows. We have to distinguish various cases. So let's start like this. So I look at the HK and HKL entry. Then I have a stochastic term, the BKLT, so that's a Brownian motion, and then 1/2 HKL dt. That's for K smaller than L, and all of this first part I will have beta, so to say, the analog of the beta equal to 1 case. So now on the matrix level, we will only look at beta equal to 1 or 2, and in this Dyson-Brownian motion business, and actually all betas make sense. And then I have something for the diagonal. They have a slightly different variance. There's a different coefficient of the Brownian in front of the Brownian motion, and the rest is the same. That's what I want to call L, and then for K equal to L, and then for when K is bigger than L, I just impose the Hermitian symmetry or the real symmetric. So that's K bigger than L. So that's one set of equations. And the alternative is when the beta is equal to 2. It looks a little bit more complicated because now, of course, we want to have something just truly complex. So I have the HKL is equal to 1 over square root of 2n. Then I have a dBKL1t plus I, so that's now the complex unit, dBKL2t minus, and then the same as before, 1/2 HKLT t. So that's the case when k is smaller than L. Then the diagonal is as before. There's a, but now again with the normal variance. So the normal coefficient t minus HKKT dt is L. And then the emission symmetry, so HLK of T complex conjugate. Okay. And yeah, all of this system together, since it will come up many times now, I want to call it MSTE. So for that's the, well, the most important matrix valued stochastic differential equation that we will consider. And I should say something about the Brownian motions, namely they are, as you would expect, they're all independent. So BKL when K is smaller than L are independent Brownian motions for beta equal to 1. And then I have a bit bigger set, so BKL1 when K is smaller than L. And then the union would be BKL2 when K is strictly smaller than L are independent Brownian motions for beta equal to 2. Okay, I hope this, yeah, so just like this, it all fits on one picture, so you can maybe take a snapshot of this. And then I want to introduce some shorthand notation for this, so then if I ever have to write it down again, then I don't want to, of course, not write this whole thing again, but but we have some bit shorter notation. I want to write dHT equals to 1 over square root n dBT beta 1/2 HT dt beta equal to 1, 2 shorthand for this long MSDE. Okay, and now the result will be that it's the following theorem, which goes back already to Dyson, to the 1960s. So beta is again 1 or 2. Here we have to restrict ourselves. And then if I start from a strong solution of the equation above, we can you can easily check that it has the solution by invoking the the results from the last lecture, because the yeah, maybe that's a good point which I should start now. So of course this system of equations has a unique strong solution, because the coefficients only grow linearly in h, and there's no time dependence and nothing. So you can directly apply the results from the last lecture, so that you get strong solutions in both of these cases. So this uniqueness and existence of this is clear. For the other equation, for the Dyson-Brownian motion equation, it's not clear, because the coefficient, they have this singularity, is 1 over lambda I minus lambda j term. Maybe I should have said that before. That can of course blow up if the solution comes too close to each other. So this one has to control separately. That's why this is a non-trivial theorem. But the existence and uniqueness of these equations is really given. That's not an issue. And now the point is that once we have a solution, we get a solution to the other equation as well. The strong solution of this, and then well, I have to fix some initial condition. So H0 should be in R and symmetric for beta equal to 1. And H0 can be complex, which is complex emission for beta equal to 2. Okay, so we have these two solutions, and then I look at the eigenvalue process of this HT. And then the eigenvalue process of HT is a weak solution. I'll explain in a minute why we can only expect a weak solution. For this beta. Okay, so what does that mean? So, well, I start with a solution to this matrix valued stochastic differential equation, and then I look at the eigenvalue process. So well, by definition, the solution is again Hermitian, so I have real eigenvalues, and then I can look at the system, at this DBM system that we had before, and in fact, it turns out then I get a weak solution, because I have to, well, I cannot fix the Brownian motion, but the Brownian motion will come out of the Brownian, will be somehow a combination of these Brownian motions here in a certain sense. But in that sense, I then get a weak solution, because the Brownian motion has changed, of this DBM system for beta. But for weak solutions, we know that at least they have the same in law. And of course, for eigenvalues, well, we're interested in these local statistics or any kind of results, but we are interested in them in a probabilistic sense. So this distribution, that's the main thing we're interested in. And maybe I should say that we have a heuristic derivation of this theorem. So under certain assumptions is on the, or was already on the homework. So I think it's exercise 6 of homework 6. So we will hopefully manage to do that today in the exercise session. Okay, so that's the second main result, which tells us that if we can understand, or well, if we evolve this, if we evolve such kind of, if you look at such kind of Brownian motion on the space of matrices, Then if we look at the eigenvalues corresponding to the solution, then we get a solution of the DBM. So that will be a way to then analyze, as we will see in the next weeks. That will open us a way to analyze these H0s here. So the initial conditions, if we evaluate, if we evolve H under this MSDE flow, and then we can study the eigenvalues via the DBM equation, and that will give us a new way to prove universality, and which we'll then combine with what we've seen in the first weeks. Okay, so that's the outlook. So maybe now is a good time to take again a snapshot, and then now what I want to do next is to look at the proofs of to go through the proof of this lemma of this theorem 3.15. So we want to look at the existence and uniqueness of the DBM here. And yeah, as I already indicated, the main problem is here that they have this term which might blow up if the solution, if two eigenvalues go too close to each other. Or I mean, it could even happen a priori, that's not excluded, that the eigenvalues started sticking to each other at some point. But of course, this will not, well, we will actually prove that this will not happen just because of we have this repulsive interaction that I showed to you. So if they really come close, they repel each other, as I indicated in the heuristics. But this one has to track carefully, and in particular, there's also the problem that initially we might be in the situation where the eigenvalues are the same, or where I have at least two coinciding lambdas. So that could of course be a problem, and this one has to deal with, and this is the main problem in the proof, and that's the reason why we cannot apply this existence and uniqueness results directly that we started with last time. And okay, so now around half an hour left. Let me see what is the best way of doing this. So yeah, so maybe we start with yeah. So the next subsection. So I think it should be 3.3. That's the proof of. Will be devoted to the proof of theorem 315. Okay, and as a first lemma, I want to look at the following. So I think this is 317. Yeah, maybe I should start with explaining that. Yeah. We need two auxiliary for the proof of this theorem. And the first one will compare two solutions of this DBM equation. So so I have lambda and eta. There should be two strong solutions. Well, of course, with respect to the same filtration and the same Brownian motions, and then we want to compare them. And for now, I want to assume that that they all have distinct, that all eigenvalues will stay distinct from each other, such that I call of eigenvalues or particles. So the components are all of the lambda and eta. They should all be distinct for all t bigger than 0. And in the next step, we will see that that this will actually be automatic. So that will be the course of the next lemma. So and here we want to compare what the solutions do if I know a priori that they are somewhat ordered. So I want to assume that the components of the lambdas are smaller than the components of the etas in the entry-wise sense, so that lambda I at 0 is smaller than eta I at 0 for all I that go from 1 to n. And now the statement is that this ordering is kept by this DBM flow. So the probability that lambda I at t is smaller than eta I at t for all t bigger than 0 and all I from 1 to n, this probability is 1. Okay. So what does that tell me? Well, it tells me that if I have two solutions, that first of all, such that all eigenvalues, such that all components are different from each other, and such that initially they are ordered in the sense that lambda I is 0, that is smaller than eta I, sorry, for all components, then under this evolution DBM, this property is kept. Okay, and the proof goes as follows. It's actually also an argument in some sense by contradiction, and it's a contradiction where I introduce some special kind of stopping time. So now I call the stopping time big T. Let that be the first time at which lambda I of t minus eta I of t vanishes for some I in 1 up to n. Okay, so maybe a bit more formal. It's again well, this will be a stopping time, as I already said, but it's again in the spirit of this example that I had before. So I will write it down. So it's a maximum I from 1 to n. And then I take lambda I at t minus eta I t. It's a maximum, and this should be 0. So there's no, these are parentheses, that's not an absolute value. So yeah, maybe you can take a snapshot in the meanwhile while I explain what is happening here. So of course, initially, so for t equal to 0, this thing here is negative, and of course one can also assume by the solutions will be continuous. By continuity, they will be so strong solutions are always continuous. So this is also this will be continuous in time. So this will, at least for small times, will be negative. But then at some point, it might happen that two components will start coinciding, and then that will be the point where the maximum of them, so this is negative, so the maximum a priori is also negative, at least for small times, but at some point it might vanish. And that's the time which we want to analyze, and of course this is a stopping time. So this is a stopping time, and then the main goal will be that actually we want to show that this stopping time is infinite, and we will actually do that by some kind of proof by contradiction. And this goes as follows. Okay, so that will be the overall goal. And the first thing we want to show is that it's actually positive. Well, that's actually quite quite trivial. That's I already said before, that's somehow just continuity. So since the lambda I minus eta I is continuous, of course, like in the sense of past, so in time, so the paths are continuous, and we know that the maximum is, so we know that I take the maximum over I of lambda I of 0 minus eta I of 0, where it's the maximum over finitely many indices that are all negative, so this has to be negative. So I already know that the t is positive. So that's simple. That proves claim 1. Yeah, and now we will do a small computation that will be also well, computations of this type will reoccur in throughout the next lectures, well, throughout maybe the rest of the course even. And what we want to compute is actually we want to compute how these differences lambda I minus eta I involve in time. Okay, and yeah, maybe I should just, doesn't harm to recall this DBM equation again. So it's 2 over beta n dBi plus minus lambda I over 2 plus 1 over n sum j different from I lambda j dt. And then of course we have the same for eta I, where all etas are all lambdas are replaced by eta. And then we can just subtract both of these equations from each other, and then we obtain the following. It's d lambda I minus eta I. And that looks as follows. So there's the very nice thing is that will be very helpful in all of the following is that this term here drops out. So the eta I has the same the eta I follows an evolution with respect to the same Brownian motions here, and there's just a constant coefficient, so this term drops out. So we will only get a time. We will only get an equation which has a time contribution, but of course the lambdas and the etas, they will still have random. Will be random, but their difference is somehow, in some sense, evolves deterministically. And it evolves with respect to the following equation, j different from I, and then here I can put these things together, and what I end up with is, I guess if you sit down later or second, then you immediately see this. You'll get the following term, and then lambda I minus lambda j, eta I, eta j, dt. Okay, so maybe now's a good time, and this I want to call 1. It's maybe a good time to record this. And what does that tell us? Well, it tells us that the difference of lambda I minus eta I, this evolves in a deterministic sense. So in the sense that, well, I have a random coefficient, but just the randomness of the lambda I and eta I comes into the play, and there's no other randomness which comes from the Brownian motion, that at least not directly in the evolution of this difference. And so I hope you took a snapshot now. And what we what I want to show next is that along the whole flow, the lambda I of the sum of the lambda i's minus the eta i's, this is negative. So that already indicates that, well, that's of course a weaker statement than what we want to prove, but that will actually be helpful in the proof of the rest. So the claim 2 is now that sum over I lambda I of t minus eta I of t, this is smaller than 0, well, of course in almost sure sense, for all t bigger than 0. Okay, so that's the claim. And to prove this, we define now this difference of the sums I want to call dt, d of t. So sum over I lambda I of t minus eta I of t. And then we of course need an equation for this, but this is easy to do because we can just sum up. Well, maybe summing up 1 over I from 1 to n, we get the following. So d of dt is equal to 1/2. Well, then of course we have the sum of this term. So it's, let me write it like this, minus 1/2 lambda I minus eta I, chopping now the t dependence, plus 1 over n, sum over I, sum over j different from I, eta I lambda I minus eta j minus lambda j, divided by minus lambda j dt. Okay, so that already looks somewhat good. And the important point here is now that actually, if you stare at this a bit, then you will see that this term here vanishes. Well, why is this? So basically what you do is you split this up as in the way I already indicated it here. And then you somewhat exchange the summation indices. And then if I exchange I and j here, I get a minus. But if I exchange I and j here, then I get another minus. So this here does not change. And then I really have the same. Terms here. And then this thing here cancels. So from this I can conclude that actually the dt, the d of t evolves according to the following equation. It's well, somewhat, yeah, well, it's an honest differential equation, and it's just that initially it's the lambda and the nus are the lambda and the etas, they are random, but it means that it's a differential equation but with a random initial condition, but that's still easy to solve. So this, you can see that this is dt d of t equal to 0 e to the minus 1/2 t. So I can just directly compute what the sum lambda I of t eta I of t is. Namely, this is, by definition, it's dt. But now from this thing here, I can conclude that this is smaller than d of 0, which is the sum over the differences initially, and this is smaller than 0, so this proves my claim 2. Okay, so yeah, maybe now is a good time for another picture. And then now the third step will be directly to prove that that this time t is infinite almost surely. And that, yeah, this completes the proof of the lemma. It was now 317. And this we will do, as I said before, by contradiction. So you assume that this time is actually finite, and then you conclude a contradiction by from these identities that we used so far, or that we derived so far. Okay, so how do we do that? Well, so let's start slowly. Assume that t is smaller than infinity, but that means that we have an I in the index set 1 up to n, such that lambda I at t coincides with eta I at t. Right. So before the maximum was always negative. Then as soon as it starts being 0, there has to be one term where the maximum in the definition of the t, maybe I should go back to this, where this here vanishes. So then this component, the eta I at the big T and the lambda I at the big T have to be the same. Okay, but now I can use the identity that I had before, and that gives me some things. I will write down what I mean, and then we can go back to this. So what do I need? I need this. So this is the I will first write down what comes out, and then we go back to where it comes to 1 to see where it comes from. So I claim that the derivative at the little t equal to t looks as follows. And the important property here is that the lambda I and the eta I are the same for this time. So where does this come from? Well, it comes from here, from 1. So first, these two things here, this term vanishes because the lambda I is the same as the eta I. And also here, the lambda I and the eta I are the same. Okay, so this term here also vanishes, so that what I'm left with is a lambda j minus eta j, and then the denominator that we had all the time. And that's what I wrote here. But now I have to know, I claim now that this is strictly negative. And why is that? Well, this has two reasons. So first of all, the lambda j what is the best order? Well, first of all, I should say that the denominator here, this is strictly positive, because the lambda, so the vector lambda and the vector eta, they are both, even at time t, they're in this sigma n, right? So maybe it's best to start with this. So eta I minus eta j times lambda I minus lambda j. This is bigger than 0 for all j different from I, as lambda t and eta t are in the sigma n by assumption. And then of course you have the usual, and they are ordered. So whenever lambda I is smaller than eta j, then also, sorry, when eta I is smaller than lambda j, then lambda I is also smaller than lambda j. So the product is always positive. So that's the first part. So I know already that these are positive, and I know that these lambda I minus lambda j are negative. So let that's the other thing. So lambda j of t minus eta j of t. This is, well, at least not positive for all j. This comes just by the definition of t. So sometimes the definition of t means that this is the first time where the lambda I minus lambda j are not strictly, where the maximum of them is not strictly negative anymore. So that means I can estimate, what was this? So that means I can estimate this sum here by, so I can, well, take the minimum of them, pull this out of the sum. So it's 1 over n times the 1 over the minimum, the minimum of 1 over these coefficients here. And then I have the sum over the lambda j's. But then I can use claim 2 to prove that this inequality is actually negative. So, and together with claim 2, this now proves this inequality here. Okay, but now we can go back. So since the lambda I of t minus lambda eta I of t is smaller than t for all times that are smaller than my stopping time, I can go a little bit back by continuity, and then that means that I could have never reached this. And by continuity, the right-hand side of 1. So that means that the derivative here had already been negative before, so I could not have reached this t. I could not have reached lambda I minus lambda eta I to be 0 at that point, and that means that the t has to be 0. Okay, so I think I guess you already took a snapshot of this. If you haven't done, then maybe do that now, and then you can take another snapshot of this claim 3. So what we have proved now is that this Dyson-Brownian motion flow preserves the order of the eta I minus lambda, preserves the order of 2 vectors. So if initially all vectors were ordered, all components were ordered in such a sense, then this is kept under the flow, and this will allow us that in the sense in those situations where I don't have strictly ordered entries, I can move them all a little bit such that I get an ordered thing, and then I can evolve the flow, and then once I remove this thing, the order is kept, so they can converge to the right thing. This is what we'll see in the proof of theorem 315. And then now there is another lemma, which I still want to state, and which we will then only prove next time, actually. And that tells me that, essentially tells me that the statement of theorem.
Can I ask the question about this proof?
Yes.
How did you use claim 2?
The claim 2 is, so, okay, maybe I can explain this a bit better. It's, so it's, I use the claim 2 because this here I write as a sum over the lambda. This here essentially, well, let me write it down. That's maybe a good point. So So I have to estimate this sum here. And so because these here are all, they're all non-negative. Did I do a mistake here? So I want to estimate this here from above by, well, okay, I can estimate, isn't this correct? So it's, I now have to take the minimum of these, I different from j, lambda I, well, I think it's correct. So lambda I minus lambda j times the sum times this sum, right? So it's meant in this way. But then this minimum here is positive. And then this here is negative by claim 2. But I mean, of course, this is the same as the, this is the same as the sum over all j, because the eta j and the because the lambda I is anyways the same as the eta I, so this here is strictly negative, and well, this here is negative by claim 2.
Every term here is negative, right?
Sorry?
But we know that every term here is, okay, we know that every term is not positive.
Yeah, we only know that it's, I mean, the danger is that here I only get 0. I mean, of course, it's clear that this is not positive, but the danger could be that it's 0, so I approach this very slowly. And here it's important that I really have to prove that it's strictly negative, and for that I need that at least, I mean, in some sense I have to prove that at least one lambda j minus eta j is negative. And
okay.
That's what I use this claim 2 for.
Yeah, okay, thank you.
So maybe I can, so yeah, maybe if you want to, so I think this seems to be correct now. So this gives this step. So well, maybe this is a good time to stop, and then maybe I should just give an outlook for next week. So next week we will actually prove this theorem 315 by first proving a lemma, which proves the whole theorem if the initial condition is actually inside the set sigma n and not in the closure. So it's a more special, well, it's of course a weaker statement, but that will be easier because then we have already initially, we know that all components are different, and then we can prove that along the flow this is kept. And then in the proof of the theorem 315, we then combine this, this statement for the weaker case and this ordering lemma that I proved now to conclude this 315. So that's the project for next week then. So if there are no questions or comments, then I would suggest we make a short break to, yeah, let's say 11:15, and then we can continue with the exercise session.